All right, so for today's lesson, we are starting section 3.4, and the title of this lesson is Linear Programming. And this is a very common, I guess you could call it a technique that's used especially in the business world. It's probably used in other places as well, but a lot of times this is used in business. And the primary use is to help us, especially in businesses that make things that are going to be resold. It helps us get an idea of the combination, the correct combination of items that need to be made in order to maximize profit. Obviously, that's what businesses are all about. They want to make the most profit as possible. Or the flip side of that is businesses are also looking for ways to minimize cost. Okay, those two things are of primary importance for a business. We want to make money, and while we're doing it, let's keep our cost at a minimum. And that's really, in a nutshell, a big overview what linear programming helps us do. So I thought I would just walk you through what might be like a real life problem, and we're going to let linear programming help us solve it. So I've color-coded to kind of help us keep these items straight. We're going to be writing some inequalities to represent each of these colored statements. Okay, so first of all, let's just get some context with our problem. We're making tables and chairs. Okay, so I'm just going to since I've got two products being made, one product will be for each axis. Okay, so I'm just going to label the x-axis as tables. Really doesn't matter. We could do chairs here. Doesn't really matter which. So if I label the x-axis as tables, then my y-axis obviously will have to be chairs. So again, the x variable will connect to tables, and the y variable will be associated with chairs. Okay, so let's take this first red phrase. The information that we're given is that this particular company is able to make at least 30 tables a day, sorry, and we can't make more than 60. Okay, what this is in linear programming language, it represents what we call a constraint. A constraint is what you might think of as a limitation. Because of space, because of workers, money, whatever the reasons, this is all we can do in a day. We could do at least 30, but we can't do more than 60. So the way we're going to express that range using inequalities, since we're talking about tables, is like this, and maybe this looks kind of familiar to you. My tables being produced in a day will be anywhere between 30 and 60. Notice that word between. We've been used to seeing this and compound, and again, that's what that means. So since I can make 30, then these should be both or equal to. Okay, I'm going to at least be able to make 30, but I'm not going to be able to make more than 60. And I'm using x as my variable because that's what we labeled the x-axis. So let's just go ahead and draw using lines. Let's draw the line x equals 30. Now obviously I don't have 30 lines here, so I'm going to let each one of these marks represent 10. Okay, this is 10, this is 20, this is 30. So let's draw the vertical line, x equals 30. Okay, so just grab your straight edge. And remember, these are in tens, 10, 20, 30. There's the line x equals 30. And then we need to go over 3 more and draw another vertical line. X is 60. So that takes care of the or equal to part, but what do we do in between? Well, since these are inequalities, we know that we're supposed to shade. So I'm just going to shade in between those two lines. to represent my capacity, my limitations, if you will, for the number of tables that I can make in a day. And I could keep on going, but I think you get the idea. Okay, let's go to the next phrase, and I've color-coded that in blue, so I'll do this in blue. We also, when we're talking about chairs, we are limited, basically. We can do at least 40 a day, but we cannot do more than 100 a day. And again, since we labeled the y-axis as chairs, we'll use the y variable to represent chairs. Can somebody give me the similar inequality for the number of chairs that we can make in a day? Anybody want to take that? Stacy? Okay, and again, y represents chairs. So that's going to be my inequality in between 40 and 100, counting 40 and 100. That's our capacity. That's what we're able to do as far as creating chairs. So let's draw these two horizontal lines. Remember, these are in tens, 10, 20, 30. Here's where y is 40. 10, 20, 30, 40. So we'll do a horizontal line through y is 40. 50, 60, 70, 80, 90, and right at the top, we'll just say that that's 100. All right, so now we should be shading in between. Again, that's what this means, all the numbers in between 40 and 100. We've done the 40 and the 100, but now we need to show in between, and we're going to shade. Well, just like yesterday's assignment, this is a system, so we're interested in where the red and the blue shading meet, just like you did on the homework. So hopefully you can see that that's going to be right in here. This is where red and blue come together. That's why yesterday's assignment is so important for this. So right now we've got this rectangular shape that represents our capacity for making tables and also for chairs. All right, let's take care of the next phrase. The next phrase says, if we took the number of tables and chairs together, added them up, the most we could make a combination of the two would be 120. So does anybody have an idea of how we can represent that as an inequality? Tables, chairs together, at most, we could make 120. So anybody want that as an inequality? Anyone call on somebody? Chase, you look like you had an answer. How would you represent table and chairs together? Okay, that's good. Very good. Need to change this. Yeah, Chase got it. He said, let's do the sum of tables and chairs, x plus y. And we could do 120 or less, or in other words, we'll represent it as less than or equal to 120. Now, we need to graph this line, so what must be done? Ethan Carter, what do we need to do here to set this up for graphing? Very good. Get it in solve for y form. Now it's ready to graph, and I'm going to cheat just a little bit. I'm just going to go up here and make a couple more marks, because we said this is 100, this is 110, so we're going to say up here is 120. And now we just need to count a slope of -1. Well, I know these are in tens, but isn't -10 over 10, isn't that -1? Yep, it is. So I can go down 1 and right 1, down 1, right 1. And let's connect those dots, and I'm hoping I'm still going to be in good shape, even though I made up a couple of points up there. Okay, looks good. All right, and now we need to do the shading. So tell me by saying above or below, which side of this green line are we going to be shading since it says less than? Below. Okay, and once again, we're interested now in where all three colors come together. What area do all three colors share? And I'll try to make it even darker. So we're talking about this region. Okay, so the big reason why I wanted to do this problem with you using a word problem is I want to throw some terms at you that the book is going to use, and I want you to understand what they're talking about when they use these terms. This region that we've identified that's darker than anything else, it's where all three colors came together. We have a name for that. This is called the feasible region. So I want you to put that in your notes. F-E-A-S-I-B-L-E, region. So that's the area where all of our shading comes together. So when you see the word feasible region, now hopefully it'll help you make some sense of what that means. Now, there's another important part to the feasible region that's going to help us answer the final question. And it has to do with where two or more lines cross each other on the edge of the feasible region. And there's actually 4 different ordered pairs where that happens. And these points are called vertices. So let me give you a definition of vertices. First of all, it has to be the intersection of 2 or more lines, but it's not just that. It's also the intersection of 2 or more lines on the edge of the feasible region. So for example, I may have 2 lines like here. Green and blue cross each other here, but that's not a vertex because that intersection isn't on the edge of my feasible region. Okay, so let's wrap this up. We're getting pretty close. Do you see what I have italicized? This is called our profit function. And I'm kind of interested to see if you can use our variables, x is tables, y is chairs. Can you use those variables together to come up with an equation? And I'll get you started. An equation for profit. We'll just call it P is what? Okay. Do you mean, good. He's exactly right. That's how we're going to determine profit on the number of chairs and tables that are manufactured. So here's the final step in this process. We want to know how many tables and chairs should they make per day to maximize profit. Well, here's how we're going to know the answer to that question. Each one of these vertices, let's just go ahead and name them by ordered pairs. Let's just start with this bottom left one. What is the ordered pair of this vertex? That's just singular for vertices. Can you tell what that is? Looks like 3, 4. Now remember, we're in tens, so don't let that mess you up. That's actually how many tables? 30. And how many chairs? 40. But we're just going to write it for space sake as 3, 4. But don't forget, each of these units are in tens. So how many tables and chairs up here at this vertex? What does that represent? Well, it's 30 again. We'll just put 3. And how many chairs? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's like 90. Okay, what about this vertex? What's the ordered pair? Let's see, 1, 2, 3, 4, 5, 6. And then 1, 2, 3, 4. And so this last one here must be 6, 6. And I'm running out of space, but Hopefully you can see that. Okay, now here's your job, and I'm going to give you about, if you want a calculator for this, you can use it. I want you to take each of your 4 vertices, and you're going to plug in the appropriate. Now remember, you're not plugging in 3 and 4, you're plugging in 30 and 40. Okay, that's very important. You're plugging in 60 and 40. I want you to plug those numbers in for X and Y, and I want you to tell me which of the ordered pairs, which of these 4 ordered pairs gives us the highest number for P. P stands for profit. Okay, so test each one. Now let me give you a word of warning. Some people will just say, well, that one's the highest, so it must give us the maximum. Well, you can't always go by that, because if you notice, the multiple for Y is less than the multiple for X. So don't get caught into the trap of, I'll just go with the one that's at the very top. It doesn't always work that way. So I want you to test the 4, and then we're going to come back in just a minute, and I'm going to have you tell me which of those 4 gives us the highest value for P. And don't forget to use multiples of 10 here, like 30, 90. All right, I'm going to pause, and then we'll see what you come up with. Did it not start? Okay, so what we've determined here is that the vertex that gives us the highest value for P is this vertex here that really should be 60, 60. A combination of 60 tables and 60 chairs. When we plug those numbers in for X and Y, X is 60 and Y is 60, we get a profit of $12,900. And you can see the other vertices, when we plug those in, we got lesser amounts. Here, I've just shown the amounts that we get each time we plug in the associated ordered pair into our profit function. So the answer to our question is, how many tables and chairs will maximize profit? Well, it would be 60 of each. And what is that maximum profit amount? It'll be $12,900. So that is a real, like a real life example of linear programming in use. And now let's do a couple of examples that are like your homework problems. So this is provided for you on your notes that I gave you. So here is our system of constraints, okay? Notice on our word problem, we had to come up with the system of constraints based on the word problem. But for tonight's homework, the system of constraints will be given to you. So let me just do this red inequality first. So remember, these are vertical lines. We have 2 vertical lines that will be shaded in between them. So here is the line X is -2, vertical, passing through -2 on the y-axis, and then another vertical line passing through +4, I'm sorry, on the x-axis, and then vertical passing through 4 on the x-axis. All right, and I think I'm just going to wait until the end and we'll do all the shading, but if we were to shade at this point, it would be shading in between these 2 red vertical lines. All right, so now let's take a look at this blue inequality and how it would look like when it's graphed. We need a horizontal line at y is -1, right there. And then another horizontal line at y is 3, right there. And shading between those 2 blue lines would be this way, but so far we're shading between the red, also between the blue. So at this point, you can kind of see that we're double shading. Our red and blue shadings come together in this rectangular area right here. Okay, well, now let's do the green linear inequality. All right, change my color. And this has a y-intercept of 5/3, which is just another way of saying 1 2/3. All right, so here's 1, and we should put a dot just below 2, 1 2/3. And then from there, we'll do a slope of negative 2/3. So that's up 2 and left 3. Or we could do down 2 and right 3. All right. So here's the boundary line. And now we'll do the shading. Okay, so let's see if we can think about how all of this shading comes together. We're between the red, but also between the blue. So we already said that we knew before we drew the green line, we were shading in this rectangle. But this green line kind of splits this rectangle up, and we're going to shade above the green line. So the shading where all three come together is above the green, below the blue, and then to the left of that red vertical. Okay, so this would be, again, the term that we use for this is our feasible region. Not that you have to identify this on your homework. I just want to make sure that you're familiar with that term. And it's important to know because from the feasible region, we're going to get vertices. And in this problem, there are 3 of them. Remember, intersection points, 2 or more lines that cross each other on the feasible region. So it looks like we have a point of intersection, a vertex here at -2, 3. Down here at 4, -1. And then up here at 4, 3. Okay. So those are our vertices, and now the problem says that we're supposed to both maximize and minimize the given objective function. And the one that's given to you is p equals 2x plus 7y plus 4. Okay, so let's test each one of our vertices, and we'll see which of these vertices gives us the highest p and then which one gives us the lowest. So I'll just start here. I'm going to plug -2 in for x and 3 in for y. And simplify this. So this is -4 plus 21, which is 17, plus 4, 21. Okay, let's do another vertex. Let's just do this one in here. X is 4, and y is -1. All right, this is 8 plus -7, which is 1, plus 4 is 5. And we got one more. So x is 4, and y is 3. So this is 8 plus 21, which is 29, plus 4, which is 33. Okay, so the ordered pair that gave us the maximum value for p is this one, the ordered pair 4, 3. And the one that gave us the minimum, the smallest number for p, that ended up being the ordered pair 4, -1. And so we are finished with that problem. And so let's just try one more, like your homework, very similar to what you're going to do on your homework. So we got 1, 2, 3, 4 different constraints with shading that we need to do. And then let's see if we can determine where all 4 shadings will combine together. All right, so let's do the red first. That has a y-intercept of -3 and a slope of 3/2, up 3 and right 2. And we'll do that one more time. And let's draw this boundary line. Looks like that. Okay, there's the red. I'm not going to shade it yet, but maybe I'll just put some arrows to indicate which direction we'll be shading in red, and greater than is above the line. Okay, now let's do the blue. It has a y-intercept of 7, 2, 4, 6, 7, and a slope of -1. All right, so there's the blue boundary line, and maybe instead of just shading it right away, we'll indicate which direction we'll shade. Less than is below the line. So right away you can see that we're talking about this region. Now here's a couple of interesting constraints, and this happens a lot in real life when we're doing production. When we're producing two products, it's not possible to produce a negative number of anything. So these usually stand for production materials, where we're just saying we're either going to produce nothing of that product or it's going to be a positive. So the effect of these is to essentially keep our shading confined to quadrant 1. So let's just start with the x equals 0 line. This is where x is 0, the vertical line just right on top of the y-axis. And the shading, the greater than side for that, is to the right. So you can kind of see how our arrows are all converging together. And then we're going to do this constraint, which is y is greater than 0. Well, that's just a horizontal line right on top of the x-axis. And the greater than side for this line is above. Okay, but we're confined by this red line and this blue line. So where does it all converge? Well, it's right in here. All right, so we're going to shade it in. This is our feasible region. And from this feasible region, we need to identify vertices. And it looks like there's 4 of them. We have the origin, of course, 0, 0. We have this point up here that's on the edge of the feasible region. That's the point 0, 7. 2, 4, 6, 7. We have this point right here, which is the point 2, 0. And then we have this one, which is 4, 3. Okay, so the directions here, here's our given function, p equals -5x plus 4y. So once again, we need to test all 4 of these, and this problem says let's find the ordered pair that gives us the highest value for p, and then the one that gives us the lowest. So I'm just going to plug each one of them in. I'll start with this one. X is 0, and y is 7, and so that's 28. For the origin, of course, that's just going to create 0. All right, and then we'll do this ordered pair, 2, 0, -5 times 2 plus 4 times 0. That's -10. And then -5 times 4 plus 4 times 3. -20 plus 12 is -8. Okay, well obviously the highest value for p occurs here. So we're going to label 0, 7 as our maximum. The lowest value is here, -10, which occurs at 2, 0. So we're going to label that ordered pair as our minimum. Okay, so maximum occurs at 0, 7, minimum occurs at 2, 0. Okay, well those are the examples, and I hope that helps you with the assigned homework that you're going to be practicing. They're going to give you the system of constraints. That's what this system is. And it's just going to be your job to graph and shade, find your feasible region, and then that'll help you find the vertices, test them in the given function. Now, your homework problems are not going to have you do both the maximum and the minimum. I just wanted to give you some extra practice. You're going to do one or the other, so just read your directions carefully. They'll tell you which one they want you to do. And if this doesn't help you, contact me, and I'll be glad to help you.